Okay, in this lecture, we're going to be going over the final project worksheet, or workbook rather, and I'm going to bring you through each of the individual tabs on this Excel workbook. You'll notice that there are quite a few tabs, but for you, for your actual workbook is only going to contain 5 tabs. Here's an example of the final workbook example for the actually, let's do this is the example of the final workbook, the way that you're going to see yours. There's only going to be 5 tabs on the bottom, and you guys are going to submit as a group. You're going to submit one of these collective workbooks together. But I'm going to walk through the example because what I do is I give you an example that is completely finished, so that way you'll have a really good understanding of, hey, this is exactly what it is that I need to be turning in. It needs to be very similar to this, and so that way you'll just have a model to work from. And also you don't have to ask anyone else, hey, how do you do this, or what does this look like, because I already give you what it looks like. So please don't ask for somebody else's work and try to copy off of their work. Don't do that. Use my work as an example, and I promise you my work as an example is going to be better than anyone else's work as an example. So the very first tab, you'll see Excel formulas. This is every single Excel formula that has to do with anything that we're talking about in this course. Some of these I'm not 100% confident on whether or not they work as perfectly as they should. I know that we went through a little bit earlier and realized, hey, there's some Excel formulas that just aren't working the way that they should. And so when in doubt, use the by hand formulas. So next, there's a tab on assumption testing. In order to run every single test, you've got to meet certain assumptions. And so this goes through, okay, your single sample, your independent sample, paired sample, goodness of fit for equal proportions, and goodness of fit for unequal proportions. And then below that it says, hey, here's what's being examined. A sample mean is being compared to a population mean, independent sample, and so on and so forth. This is a really great resource. I'd highly suggest that you just hang on to this. There's also a decision tree that if I can, I'll put it in here as well. But if I put the decision tree in here, there will be another video that goes over that decision tree. There's also a decision tree in the back of your book, so I'd highly suggest that you pay attention to that. It's a really great decision tree that tells you, hey, this is what you should choose and when you should choose it. For your actual exam, this is going to be beneficial because you've got to choose what test you're going to use when. Okay, next I have a reference sheet for each different type of test. And we're not going over all of those right now, but I just wanted to point out to you, there's a single sample reference sheet. There's an independent reference sheet, paired reference sheet, goodness of fit for equal proportions reference sheet, and a goodness of fit for unequal proportions reference sheet. And so what this does is this gives you everything that you need to know for that test all in one location. So I'd suggest that you familiarize yourself with this and know how to use this when I ask for the purpose, when I ask for the assumptions, when I ask for hypotheses, examples, effect sizes. That's all right there in that sheet. So yes. And I do spend a lot of time putting these things together. So one of my professors always used to say, he said, I didn't always read every book, but I knew that if my professor took the time to put something together for me, I should probably pay attention to that because that's probably something that he really actually cares about. And all that to be said, the reason why I put all this together is because your textbook, there's a lot of really great information in there, but I do my very best to make it as concise and manageable as possible because I know you guys aren't going to read it all. So I'm going to try to give it to you in such a way that you will. Okay, so let's go ahead and move on to what we're doing in this particular lecture, which is going over the single sample test. So for each test, what I would highly suggest that you do is have this video up, ready to go, and just, I mean, you can do this test with me, and, you know, just delete the information and retype it if you want to, or you can literally take your, which I know you probably don't have a 24-inch monitor. You might, who knows? But in all honesty, if I can be really honest with you, about getting a monitor, your productivity in the business school is going to increase exponentially. This 24-inch monitor, you can buy one for like 125 bucks. And your overall productivity is going to increase, and there are stats to demonstrate. I feel like I should make a video on, I should do a data set on increased productivity of individuals with dual monitors of a particular size. You're like, and you're a nerd. Yes, I am. We've already established that. But if you have your data set right here, and then I have my data, and you have my video up on the right hand side, that's what I would suggest you do. So that way you can watch and be able to do that. More so, I think what I'm going to do is I'm going to edit this video so that way you can leave it on this size, and so you can just have it on this right hand side, and then you can have yours on the left hand side. So let's see here. So we have this fun data analysis, write-up portion, and calculation charts and tables. I reorganized it this semester, so in the future videos, you're going to see them, you're going to see me go over to the calculations, charts, and tables on the right-hand side, but in actuality, I tried to make it much more succinct by putting it down below, so that way you don't have to go over to the right-hand side as much. I know that it's easier to go up and down than it is to go side to side when doing your analyses. So I just want to make you aware of that. So when you get your data, you're going to have your data, it's going to look something like this. You're going to have Atlanta salaries, or whatever yours is. This is all going to be blank, so I'm going to delete that. And then I'm also going to delete this. I'm going to delete this. And we'll go ahead and delete this as well. And so that way you can kind of see, hey, I'm going to walk through this step by step. Now, when you get this, you're going to see this yellow box right here. This yellow box is basically going to tell you what it is that you need to do, or what the data is that you're looking at. So this data allows you to compare the average salaries from Atlanta and the population average salaries for the whole nation. So we've got the national salaries right here, and we've got the Atlanta salaries right here. So these are more specifically, these are the average salaries for different trades. Now, if you go for this particular data set, we have, if you go all the way down to base pay data, there's something for base pay data, and what it has is these are all the different types of jobs, and these are the average salaries for individuals in those jobs. So that's what we have. We have all the average salaries for all these different jobs in Boston, in Chicago, in Atlanta, Houston, so on and so forth. So I'm taking just Atlanta. Just Atlanta. Let's see here. And I'm comparing it to the nation. So we've got the nation right there, and we've got Atlanta right here. So descriptive statistics, let's see here. So follow these numbers in a row. And you should have, you notice your numbers are right there. And then, so you've got your numbers. So follow these numbers. So it's step 1, step 2. So you're going to want to find the sample mean. In order to find the sample mean, we're going to go equals average. You're going to highlight. Okay. So you've got the average sample mean, and then you've got the sample standard deviation equals standard deviation of the sample. And I'm going to highlight the standard deviation. or for the standard deviation. Okay. So 22,614. So you've got the mean of 61,648, and then you've got the standard deviation of 22,614. And so we're going to come over here and we're going to start filling this out. Now, before you actually do any test, notice the test is all the way down at step 7. You need to have the descriptive statistics. You also need to decide, hey, what's my alpha going to be? What's my degrees of freedom? You've got to basically look at everything and determine what you can just based off of descriptive statistics first. So I'm going to have an alpha of 0.05. That means that, I'm okay with a 5% chance of saying that there's something significant when there actually isn't. So there's a 5% chance of type 1 error. The degrees of freedom is 83. So the way that I got that, I went over here and I counted these up. So you can literally highlight them. And let's see here. A lot of times if you just highlight it, yep, it says 84 rows. Or you can do equals count A, and you can highlight all of them. But there is one other thing that you could do. So that is obviously one way that you can do it. But the better way to do it is to just use the descriptive statistics tool. So every single one of these, I tell you, hey, use the descriptive statistics tool from data analysis. So I'm going to go to data. And yesterday when I was doing this, the data analysis tool was gone. And so I had to put it back up there. If that happens to you and it's gone, what you need to do is go into, let's see here. I went into options, I went into add-ins, then I went into Excel add-ins, and then it was even checked. It said, hey, it's there. So I had to uncheck it, and then it disappears. And then I went File, Options, and with Mac, it's obviously different. Add-in, and then Excel add-ins, go, and then I added it back. Pressed OK, and then it put it back up there. So if it disappears, just, take it off and put it back on. It'll come right back. So descriptive statistics. So I'm going to go to data analysis. Okay. And then I'm going to go to descriptive statistics, press OK. And then I'm going to go to the input range. And I'm going to highlight everything. Something's a little glitchy. I'm going to highlight everything. And then I'm going to say label in the first row. And then I'm going to click on the output range. Where do I want this? And I'm going to come right up here and I'm going to say, okay, I want it right here, descriptive statistics. And then I want the summary statistics. This is very important. I want the confidence level for the mean. If you have an alpha of 0.05, you want a 95. If you have an alpha level of 0.01, then you want a 99% confidence level. If you have an alpha of 0.1, you want 90. So just basically do whatever alpha you have, do the what's that called? Do the confidence interval that corresponds with that alpha. So we've got a 90, we've got a 5, we've got an alpha of 0.05, so I'm going to do a confidence level of 95. And so then I'm also going to do the largest and the smallest, in other words, the max and the min, and then I'm going to press OK. Okay, so we've got the mean, the standard error, the median, the mode, the variance, kurtosis, skew, range, min, max, which it also gave you the min and max right here, so I guess we didn't need to do the min and max, but it's there if you want it. And then this right here, very important, this is the margin of error at a 95% CI. Okay, so coming right over here, we've got the declared alpha, we've got the degrees of freedom, which if you come right here, there should be, is there even a count? I guess there's not a count. Oh, there is a count, 84. 84, so then you come over here and you're like, okay, 84 minus 1 is 83. Now we have to make a choice. Do I want to make it a two-tail, a upper tail, or a lower tail? Um, I decided, you know what? I really don't know. I don't have a hypothesis of whether or not one's going to be higher than the other. So I'm going to do a two. Um, and then do I want to do a z, t, or a chi-squared distribution? And we're going to do a z. The reason why is because we have the national standard deviation. And because we have the national standard deviation, the population standard deviation, we can do that. So the population mean is right there, the sample size, the sample mean, and the sample standard deviation. And there are these fun little formulas right here that you can use. But like I said, you can also just grab it. Well, you can't get the population information from the descriptive statistics, but everything else you can just get straight from the descriptive statistics. So that's really great. So here's the research question. And I think I'm just going to put these, I don't know. Let's see here. Do I put these in there for you? So I want to know what you're looking for. So I'm going to ask you to give me the research question. Yeah, I'm definitely going to ask you, hey, tell me what the research question is. And so this research question should reflect the fact that we're doing a two-tailed test. So are the average salaries in Atlanta, okay, different from the average salaries of the nation? Okay. The reason why I have it phrased like this is because we're literally taking the average of all the averages. Normally, you would write it as, is the average salary in Atlanta different from the average salary in the nation? But we're literally dealing with the average of averages. So we've averaged all of the salaries from all these different occupations. So it's, are the average salaries in Atlanta different from the average salaries of the nation? Okay. And so we're saying, is this mean? Is this different than this? Okay, next. Purpose of running the test: to compare a sample of Atlanta salaries to a population average salaries to determine if differences exist. Now, I want to point something out to you. You've got this single sample right here. Go to the single sample reference. So there are different purposes for this test. So you can determine if a sample is representative of a population. You can compare a sample to a population to see if there's a difference between the two. And then you can determine if a population parameter has changed. And then you're always comparing the means for here. So what I want you to do for the purpose is literally take one of these three, and tailor it to whatever your data set is. So right now, I'm comparing the sample of Atlanta salaries to the population to see if there's a difference between Atlanta and the Atlanta and the average. Okay, so if this was a one tail, I would say, are the average salaries in Atlanta greater than the average salaries in the nation? That would be if it was a yeah, if that was a one tail test. Or you could also say less than, depending on the tail. Is it an upper tail or lower tail test? And once again, with an upper tail and lower tail test, there's an example right here of how to write that. The sample mean less than or equal to, so on and so forth. So let's see here, paired. Oh, sorry, single sample. Compare, so the purpose of running the test, to compare the salaries to see if there's a difference. Anticipated outcome: we anticipate that there will be a difference between the average salaries of Atlanta and the average salaries of the nation. Okay, all of these need to match. All the tails need to match. In other words, difference, difference, difference. Okay, just different, different, different. If this says less than, this also needs to say less than, and this needs to say less than. Greater than, greater than, greater than. Make sure that they all match. Okay. Assumptions. So once again, the assumptions are all listed explicitly right here, and they are also listed with more detail right here. Okay, and then in your book they give you even more detail on all of them. So you've got your assumptions. So you know what an assumption is you basically have uh, in order to be able to run a particular test, your data has to meet certain standards, right? Uh, the data has to be right for the test that you're running. If the data is not right for the test that you're running, then your results are useless, completely meaningless. So what I'm asking here is, does it meet assumption 1? Does it meet assumption 2? Does it meet assumption 3? Does it meet assumption 4? And if there's any sort of issue, let me know about that issue right here, so that way you can address that issue before you move forward. Assumption 1, what is the one dependent variable and is it measured at the continuous level? So what is assumption 1? Great question. Assumption 1 is there is one dependent variable that is measured at the continuous level. That's assumption 1. It has to be a dependent variable that's measured at the continuous level. So what is that dependent variable? The dependent variable is salaries. Okay. So you come right over here, Atlanta salaries. Salaries are dependent on location. In other words, these salaries are dependent on whether or not it's from Atlanta or from the national representation. So coming over here, I'm putting the dependent variable is salaries, which is a continuous variable that is dependent on the independent variable location. Okay, so that's what I wrote there. So same thing with you. You've got the dependent variable. So your dependent variable is going to be whatever's right here, and it's going to be dependent on what these are. Okay, so you look at these and you're like, what are these? What are these? They're different locations, right? Yours might be, you know, something else, but you've basically got the population versus the sample, and what is the quality that makes those different? Okay. Assumption 2 is each individual observation in the sample independent from all other observations. Okay. In other words, when you calculate one value, is it going to change the other values? So you've got the this salary right here. If this salary has to be independent of this salary, these are two different salaries. And if you go over to the actual data set, you've got all of these different salaries, and so these salaries are all different salaries. They are not they are not dependent on each other. They are independent of each other. So we're good there. So what we're going to put is let's see here. All the salaries are independent of each other. That's all that you need to put. Assumption 3, there are no significant outliers in the independent variable. So for this, you need to make a box and whisker plot. And on yours, you're going to see for your box and whisker plot, let's see here. You need to put your box and whisker plot. There's a spot for it that's going to be, yeah, right here. So we're going to put your box and whisker plot right here. And in order to do that, I'm going to highlight all of this. And I'm going to do insert and box and whisker. And so make sure you put a title. We're going to say Atlanta salaries. Again, and I'm going to move it up here. Once again, I'm trying to work on just a smaller screen so that way it's easier for you to have your screen up and my screen up at the exact same time. So if you're like, hey, just make your screen bigger, I do have a reason. It's because I want to make your life easier. So I'm going to zoom in, and it's going to make my life a little bit harder, but that's okay. So review, let's see here. We're going to click on this, design, add chart element. Okay, and we are going to put data labels on the left-hand side. Now, your data labels hopefully will look something similar to this, but you also may have outliers. So what we're going to do is we are going to answer all of these questions right here. So on the left-hand side, you've got Q3, and so we're going to do equals, well, you don't even have to do equals Q3. You can literally just put 77,383. Okay. 383. And then the median is 58,677. Q1 is right down here, which is 41,611. 41,611. And then the minimum value that is not an outlier, that's going to be whatever this line is, okay? So this minimum value that is not an outlier, if there's dots down here, that's not what I'm asking for. I'm asking for this value right here that is on this line, okay? So that's going to be 23,527. And then the mean is going to be 61,648. And really, I'm just asking you to tell me, oh, there's supposed to be one more in here. This is, oh, that's where it is. Max value, that is not an outlier. Okay, that's going to be 120,207. And so how many outliers are there above? 0 outliers above, outliers below, 0 outliers below, and describe outliers, no outliers. So if you do have outliers, you would say these are the outliers below at this value and this value. These are the outliers above at this value and this value. That's how you would describe it. So 2 outliers below at 20,000 and 18,000, and then 2 outliers above at whatever. Okay. And if you have a lot of outliers, what you would say is there are, 5, there are 10, there are 20 outliers above, ranging from, so you would say there are 20 outliers above ranging from 122,000 up to 190,000, just theoretically. So that's how I would ask you to do that. Okay. And if in future videos I say otherwise, just ignore that. The reason why is because the more and more that I do this with students, the more that I realize, hey, there's a simpler way to just say, hey, just give me the range of the outliers when there's a lot of outliers. Okay. So we're going to come back over here, and I'm going to zoom out a little bit and go back up to number right here, assumption 3, there are no significant outliers. The next thing that you're going to do is dependent variables should be approximately normally distributed. In order to determine this, you need to determine the skew and the kurtosis. So we're going to come over here to skew and kurtosis. So what I want you to do, which this is really easy, you can just round it down to, I'm going to say round it to, let's do 4. So what I did is, so we got the skew of 0.4333, 1. Oops. 0.4331. And then the kurtosis of negative 0.3466. And is that a repeating 6? I don't know. If that's a repeating 6, then, well, it rounds it off at just 6. So there's a whole lecture on skew and kurtosis and violations of assumptions. But basically, you want the skew to be under 1, and you really want the kurtosis technically to be under 1, but as long as it's under 3, it's fine. Kurtosis is not something that we're nearly as worried about. Skewness is the one that we're much more worried about. So, but what you would say is because both the skewness and kurtosis are less than 1 standard deviation away from perfectly normally distributed, we conclude that the dependent variable is normally distributed. So in other words, what this is saying, these are these skewness and kurtosis values are like the standard deviation for skewness and kurtosis. And so we're saying, hey, because they're within 1 standard deviation, because they're in that center portion, that 68%, that's pretty much everything falls within, then we're doing fine with that. Okay, so for assumption 4, the other thing that I want you, or sorry, yeah, the other thing that I want you to do is I want you to make a histogram. And so when you make a histogram, I need you to come over here. You're going to go down, and we're going to make a histogram right here. And so we are going to highlight all of this information, and we're going to say insert a histogram. And the histogram is really great to show, the distribution. The one downside is when they set these levels, these class limits, they're not that clean normally. And like this right here, I don't even know what the upper limit is. But I would assume that it probably falls more in here. But this shows that it is skewed. It is definitely skewed. But it does appear to be, normally distributed-ish. And so we're able to work with this still. And so I'm going to put right here, I'm going to put distribution of Atlanta salaries. Okay, and so then when you come up here, sorry, when you come up here to the assumption testing, then you can also put in here, let's see here, according to the histogram, the sample appears to be slightly positively skewed, but overall pretty normal. Okay, so yeah, that's how you would put that in there. If it's extremely positively skewed or extremely negatively skewed or bimodal, you would also put that in there. And so this data right here is actually really good. And so we would say, note any issues you should address. And so what I wrote is, as there are no violations to assumptions in this data, we can proceed with the hypothesis test. And if you have got no violations, literally just copy and paste this into yours and move on. You don't have to rephrase it. There's not a better way to say it. Well, there might be, but when you're talking about statistics, you really want to be as brief as possible. You want to get to the point and just move on. You're like, and you should do that with your lectures. You are very verbose. You're right, I am. That's why the one lecture that's on single sample test, the one that says thoroughly explained, I literally have a script in front of me reading it because I wanted to be so concise and direct, and I wanted you guys to have a really great tool. So please watch that one. It's really good. And I spent way too long making it. Okay, test critical value. Straight up, you're going to be doing almost all Z values for almost everything you do. And the reason why is we almost always have the population standard deviation. There are some exceptions to that, especially with, with the sample, you're going to always be using the Z. But for a lot of independent and paired, you're also going to have samples that are larger than 200, so you'll be fine with that as well. But the test critical value with 95, I'm going to pull something else up really quick. Okay, so this is a really great document that I really like. So for a two-tailed test, because this is a two-tailed test, make sure that, because the critical values are different for everything. For an upper tail test, you've got these critical values. For a two-tailed test, you've got a different set of critical values. And then for a lower test, your critical values are negative. So I'm going to make sure that you have this available to you as well on Canvas. So make sure that you have this and use this. So we are going to use plus or minus 1.96 for this critical value. And remember, the critical value is basically at that threshold. The critical value is a threshold. If it does not pass that threshold, if your calculated value does not pass that threshold, then we fail to reject the null hypothesis. If it does pass the threshold, then we reject the null hypothesis. Okay. So, reject the null hypothesis. So this is the reject decision rule. Reject the null hypothesis if zcalc is less than 1.96 or if zcalc is greater than 1.96. And notice, just because I care, I literally have the decision rules right here for you. So it's like fail to reject, reject, okay? And so this is an example. So if you have a 99, it's going to be fail to reject, and then you've got plus or minus 2.56, and then reject. So you've got fail to reject and reject, and so then we're going to do the test calculated value. There are a couple different ways to do this. You guys already know how to do this, right? You literally take you calculate the mean in comparison to the standard deviation. So this is just the z-score. The test calculated value is the z-score. So we're going to do the calculated value, and if you do the z-score, you're taking the sampling error and you're dividing it by the standard error. So the sampling error is going to be equals the mean of the sample. So we're going to do sample mean minus population mean, and then we are going to divide it by the standard error. And so the standard error is going to be, make sure that you use the population standard deviation. The population standard deviation divided by the square root of the number in the sample. Okay. And so there we go. And so we've got the test calculated value of 0.9676 dot 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 dot. The next thing that we need to do is say, hey, what's the probability of this? Okay. What's the probability of us getting this score? Once again, there's a couple different ways to do this, but the best way to do this is we are going to do let's see, equals norm dot s dot dist, and then we're going to put the z-score, and then we are going to put cumulative. So the probability of us getting this z-score is going to be 0.83340, so on and so forth. Okay, but this is not actually correct. The reason why is because this right here is the probability of getting this test calculated value if you have a one tail upper tail test. Okay, so if you think or better yet, a lower tail test. So this right here is what you need to do. So you've got norm.s.dist. What you really need to do for a two-tailed test for this formula is you want to know what is the probability of getting between the point plus or minus 0.967689. So what is the probability of getting a z-score? Really what we're asking is what is the probability of getting a z-score as extreme as this or lower? Okay, so what is the probability of getting a z-score as extreme as this or lower? And when you have a two-tailed test, the z-scores that are as extreme as 0.96 is anything between plus or minus 0.96. So it'd be this whole area right here. Okay. So this is what we're trying to find out. What's the probability of being in plus or minus, or better, sorry, what's the probability of being beyond plus or minus 0.96? I don't know what I was thinking there. Okay, so what is, let's start over. Okay, so this is your z-score. Sorry, this is your z-score, and this is your p-value. So the problem is that this p-value is not actually the p-value for a two-tailed test. This right here is a probability of a lower tail test. Okay, so this is the probability of getting getting this z-score when conducting a lower tail test. So if you were conducting an upper tail test, you would do 1 minus the norm.s.dist, okay, and that would give you the probability for an upper tail test. Okay, so for upper tail, and I really should put this in here, upper tail, do 1 minus um, let's do this, 1 minus norm.est cumulative, and then for the two-tail test, hold on, two-tail, you are going to do 1 minus norm.s.dist, and then you are going to do cumulative, and then you're going to multiply it by 2. Okay, and the reason why is, probability, or a p-value, is this is the probability of you getting the value of this test calc value or more extreme. Okay, so what's the probability of you getting that test calc value or more extreme? So if you're looking at this this chart right here, and you've got a z-calc of 0.96. Okay, so that means if you're running an upper tail test, you would say, what's the probability of you getting 0.96 or higher, so, or 0.96 or more extreme? That's going to be 0.96 or everything higher. If you're running a lower tail test, it's going to say, what's the probability of you getting 0.96 or lower? So anything that's more extreme in a lower tail test is 0.96 or below, which is right down here, 0.96 or more below. So this right here is, that 0.88. This right here, going from here forward, is that 0.1665. Now, what we're doing is, what's the probability of getting 0.1 or higher, or negative 0.1 or lower? And so in order to do that, you would do 1 minus norm.s.dist, and then do the true for cumulative. And then what you're going to do is multiply it by 2. And so this is going to be your actual p-value, and I'm going to make it into 4. There we go. And so I'm going to say, what is the statistical significance? Remember, the statistical significance, this p-value, you need to look at the p-value and compare it to the alpha value. If the p-value is lower than the alpha value, then it's significant. If the p-value is greater than the alpha value, it's not significant. And so we say, because the probability of this randomly occurring, assuming the samples are equal to the population. So in other words, the probability of this randomly occurring, assuming that that Atlanta is the same as the population, is 0.33. In other words, you've got a 33% chance of randomly getting the sample. This is greater than the alpha level, so we cannot determine that there is a significant difference between the sample and the population. Because we cannot make determine that there's a significant difference, because the comparing the test calc value, test calc is less extreme than because t calc or z calc is less, z calc of 0.967 is less extreme than z crit of plus or minus 1.96, we fail to reject the null hypothesis. Okay. So the next thing that we do is I want you to calculate the sampling error. We already calculated the sampling error. I really should have put the sampling error up here because you need the sampling error in order to calculate the test calc value. But you already calculated the sampling error, and now we are going to do the margin of error. So the margin, oh, sorry, the sample mean plus or minus the standard deviation. So do the lower limit of, so in other words, one standard deviation below is this, one standard deviation above is this. And so you could put 1 SD above the mean equals, this makes a lot more sense. Once again, this is my own creation. Oh, sorry, one standard deviation below the mean. And then we're going to do one standard deviation above mean equals 84.262. Okay, and then what's the margin of error for the sample mean? In order to find this, we're going to come right over here and literally just take this. So 4907. And so we're going to say, let's see here, margin of error, MOE at 95%, CI is 4836.15. Okay, and then right down here, give me the lower and upper limit of the confidence interval, and then in yours, there's some issues. There's some possible issues with the confidence interval formula. So what you should do is I wouldn't suggest using this. I would suggest just calculating it by hand and just using the using what I showed you from. I hate it when it does that. I want these to go away. There we go. Use the margin of error formula by hand, or use that one over on the left-hand side, which I'm assuming you're just going to use this to give you the margin of error. Okay. Let's see here. Now, I'll be honest, this margin of error, I'm okay with you using this margin of error. This margin of error, though, is the margin of error that is based on the sample standard deviation. It's not based on the population standard deviation. So if you calculate it based on the population standard deviation, it's going to be different. So just be very aware of that this is the margin of error for the sample. But I'm, for this semester, I've already got this all set up this way. So just go ahead and use this this way, and you'll be fine. But I'll also calculate it for the population. So if you calculate it for the population, I'll accept either answer for this semester. Let's see here. Effect size. No, effect size is really important. And I should have been going through this with you guys. On the left-hand side, like I said, it says, all these different steps. But I really like going fishing. I don't know if you guys like going fishing. I'll be honest, the reason why I like going fishing is because my life is way too crazy, and I don't really care about catching the fish. What I care about is sitting there on a boat and just chilling. I remember growing up and going fishing with my dad. My dad's like, catch a fish, you gotta catch a fish. And I was like, Dad, just take a breath. We're out here on this beautiful lake, and I just want to chill. So this is a picture of me, or this is a picture at my favorite lake. This is my uncle's lake. When I say my uncle's lake, I literally mean he's one of 3 people that has property on this lake. And so when you go out on this lake, all that you want to do is sit there and chill. And this is called Bass Lake. And there's a lot of bass lakes up in Wisconsin. And this picture, literally, I took it with an old junky cell phone. This is a picture from 2010. So think about the cell phones that were out in 2010, and you didn't have filters. You literally just see this amazing reflection, and all that you want to do is go out there and chill. So when you go fishing, you've got to make some choices. And I'm going to show you, let's see here. This is also just that whole area up there. But you got to make some choices before you go fishing. You're like, hey, I'm about to go fishing, and I want to go fishing for a bass. This is my best friend. His name is Jason, and so he wanted to go fishing for a bass. So he went to Bass Lake to go fishing for a bass. So think of it like a fishing trip. You're about to go fishing, and you want to tell me about your plan for fishing. You want to tell me, hey, I want to go fishing. I want to go fishing for bass. I want all this information about what it is that I'm planning on doing. And so you're describing your fishing trip before you ever go on it, and you're planning it. Then after that, you say, okay, this is what I'm looking for on the fishing trip. I'm going to be looking for this. This is the reason why I'm going. This is what I'm anticipating that I'm going to get. So when I go to Bass Lake, I'm going fishing and I'm planning on catching a bass, and this is how big of the bass that I'm planning on getting. Now, when the lake is overfished, that means that we're going to have less bass, but when the lake is underfished, that means we're going to have a lot of bass. Then the next thing that you're going to do, you're going to make sure that you're at the right lake before you launch your boat. You get there and you're like, hey, I want to go fishing for bass. And then you get there and you're like, okay, looking at everything, I realize now, oh, wait a second, there are no bass in this lake. Even though it's called Bass Lake, there's no bass. Maybe I should go someplace else. And you're checking to make sure, okay, is this the right lake for me to launch my boat in? Is this the right lake for me to be able to accomplish what it is that I need to do? Next thing that you need to do is determine what is considered catching something before you start. As much as I love this fish, it's a great fish, really great looking fish, I promise you that fish is way too small. You look at that and you're like, hey, that's great. This is a 12-inch fish. It needs to be a minimum of 15 for us to be able to keep it. And so it's like, yeah, we caught something, but we didn't catch it. And so you need to be able to say, yes, we caught something. Yes, we caught something. And if you get past this null hypothesis, or sorry, you've got the null and alternative, which once again, you're going to see the 0 and A for alternative, 0 for null, 0 meaning that there is no difference, A meaning that there is a difference. You might also see 1, H sub 1 for the alternative. So 0 for H sub for the null and 1 for the alternative. And then you caught something. What did you catch? So you describe everything that you caught. Was it significant? Did you actually get something in comparison to what you were actually looking for? And then last but not least is what you caught worth keeping. Yes, you caught something. You did. But it's not worth keeping. It's not worth it. Send it back. Wait for it to get bigger. Well, sometimes it never will. But that one's not worth keeping. So effect size. What you're going to do for the effect size is you're going to come over here and you're going to put all your information in right here. And I'm going to put the mean. So the mean of the sample. So equals the mean of the sample. And I'm going to come, oops, equals sample mean. And then I'm going to do the population mean equals the population mean. And then the population standard deviation equals population standard deviation. Okay, so I've got all those values in there. I just like putting the values in there, having it right there so that way I can do all the calculations at one time. So now I'm going to do D equals, and then I'm going to do equals ABS. ABS stands for absolute. Okay, you notice those bars right there? That stands for absolute. Mean minus the sample mean minus the population mean. Okay, then we're dividing it by the standard deviation. And this is the effect size. Okay, effect size basically says, is what you caught, is it worth keeping? Okay, is what you caught, is it worth keeping? And so you come right over here and you're like, okay, this is a small effect size, medium effect size, large effect size. Small effect size basically means what you caught, you can barely tell that it's even there. You can barely even tell that there's a difference. And really, these effect sizes, you're really only supposed to calculate them if you caught something, okay? If you found a significant result. If you found a significant result, then you should calculate it. However, I'm just going to have you calculate it no matter what. Um, so, but if you found something, is it worth keeping? And so if it's small, you can't really tell the difference. Medium, you can tell the difference a little bit more. Large, you can really tell the difference. In other words, small is like, hey, you know what? Here's the difference between the height of a basketball player and the height of a volleyball player. There's not much difference, but if you put a whole bunch of them together, you might be able to tell that there's a tiny little bit of a difference. Medium, what's the difference in the height between a basketball player and a soccer player. Basketball player is definitely going to be higher, taller, but may not be always noticeable. And then last but not least, you've got like the height between gymnasts and a basketball player, and there's right away you can tell just by looking at them, you're a gymnast, you're a basketball player. So large is really noticeable, medium is kind of noticeable, small is you can barely even notice it. So here we've got a small effect size because 0.10 is less than 0.2. You really want it to be 0.8 or above. And so we're going to come over here and we're going to put in the effect size of 0.106. And then let's see here. So you've got the effect size 0.106, and then you're going to come down here and you're going to write everything out little by little, okay? And you're like, okay, what do I write in here? Great question. So the whole point of this is you need to be able to have a narrative of what it is that you just did. Tell me, what did you do in a paragraph? And is it something that I should actually even care about? And so you follow this just step by step, okay? So it says, what was run? It says, a single sample hypothesis test was conducted to determine the average salaries in Atlanta if the average salaries in Atlanta are different than the average salaries in the United States. So literally I said, this is the single, this is what was run, the single sample hypothesis test. That is why it was run. And then what was the result? So to determine that the salaries, oops, I know why it keeps doing that, of, let's see here. According to our results, we are not able to determine that the difference in salaries of 2,037 between the United States and Atlanta is actually different. So there's a difference. That is the difference. So there really is a difference, but it's not a significant difference. It just happened by chance. The probability of these results occurring randomly in the same population is about 33%. The large range of possible outcomes contributes to our inability to determine if there's a difference. So what was the result? What is the probability of that result? You notice I have that in there. And then give insight about the factors that influence this. So you know this. If you have greater, what's that called? If you have greater, a large standard deviation or a large variance, if your data is really spread out, which this is a pretty large variance or a pretty large standard deviation, this standard deviation is literally a third of the sample. So you've got the sample mean, let's do this, equals the standard deviation divided by the sample mean, 37%. It deviates by 37%. And so that is a huge reason why you have the result that you have. The large range of possible outcomes contributes to our inability to determine if there's a difference. We are 95% confident that the actual average salaries of employees in Atlanta is between $56,811.60 and $66,483.90. So right there, I've got the confidence interval. Notice right here it says talk about the confidence interval or standard deviation, whichever one's more important. Then mention how noticeable the results truly are. So in other words, the effect size, and then how should these results be used in regard to the research question. Okay, so it says right here, because the average of the population salaries of 59,456 is well within the range, we are confident that the average salary, uh, Atlanta salary is in, we are unable to determine if there's a difference. Oh, because the population salary is within the confidence interval of the Atlanta salary, we're unable to determine if there's a difference. Furthermore, even if there was a difference, the difference would be so small that we would require statistical techniques or a large sample size to even notice the difference. These results were not able to indicate that there's a difference between the average salaries in Atlanta and the United States or the nation, so therefore they should not be used to demonstrate that there's a difference. We didn't test to say that they were the same, so because we didn't test to say that they were the same, we shouldn't say that they are the same. But if that is the initial purpose of your test, then you can say, you know, our sample demonstrates that we are not able to update the population mean because the it happens to be, you know, within that same you know, confidence interval. It's not a statistically significant test. So they are still the same. Yeah. So that's pretty much how you write this up. I'm hoping that you guys were able to literally write it up as I was going through it. And if you have any questions, please reach out via GroupMe. That's really the best way. Also, if you have questions on something, don't ask me questions saying, hey, I don't know how to do number 5. I'll be honest, I don't know what number 5 is normally when you're talking about it. If you take a picture of it, or say, give me more details than just tell me what number it is, that's going to help me to be able to answer it. A lot of times when you say, hey, I don't know how to do number 5, I look at it and I'm like, I don't even know what number 5 is. And so the more information you give me in there, the better, and I'll be able to help you out. Cool. Yeah.